Folks, I am going to start directly so I will address number 11 from 2.3, but let's just review the rules that we learned yesterday, and then we'll do 11 from 2.3. So I'll keep that in mind. So I'll start reviewing quickly here, so everybody is on the same page with material. All right, I have extended the screen to the entire screen here as far as my my screen allows. Okay, move this up here. So all right, so yesterday, so rules for derivatives. We learned these rules, and here's what they were. So the first one that we learned yesterday was that if you do the derivative of x to Vn, where n could be anything here, an integer or a negative number or a fraction or something, then the derivative of that is, and that's really important, super important. In fact, I want everybody to understand that without knowing this rule, nobody will believe that you actually took calculus 1. So, so the derivative is n x to the n minus first. All right. So this is the derivative, and then based on this, so this is the rule there, right? Based on this, along with facts like the derivative of a constant function is 0 and such, you can combine this rule with there's a couple of other rules. For instance, if you do the derivative of a sum of two functions, we said that is going to be the sum of derivatives. So in other words, you can split up a sum of two functions if you want to, for the purposes of doing derivatives. And likewise, the derivative of a constant times a function, if you want to do the derivative, simply take the constant out and then do the derivative. So we did yesterday we did problems, I think 1 and 3, yes, 1 and 3. And there's a few other questions there that might be useful before we do number 11. So I'm going to do yet another type of review question. So I'm going to do 5 and 7, and then we'll jump to 11. So so let's do number 5 from section 2.3, because it's important, folks, to have these problems done. Again, these are problems from the homework. I expect everybody does the homework, but again, if you are willing to take this route, you can try the problems. If you can't do them, then you can see how I do them on the video here. You can watch the lesson, and there we go. So you have some backup here. So the problem here is f of t equal to 2t cubed minus 3t squared minus 4t. All right, so how do you do the derivative of that? So the derivative of this f prime, can say f prime of t or just f prime. All right, folks. So we did find. Oh, I'm sorry. Oh, yeah, we. Okay. So let's do this again. Just a quick review here, folks. So I need to build on something. Thanks, Sammy. So the derivative here, very quickly, folks. Again, for the derivative of 2t cubed is 2 times 3 times t squared. For the derivative of this of 3t squared, so it's going to be minus 3 times 2 times t to the 2 minus 1, right? Minus, and then there's 4 times because t prime is 1, right? X prime. So this ends up being 6t squared minus 6t minus 4. This is the derivative of this particular function. And building on that, I want to, so my goal was to start with this and then go to 7. So sorry about that. I forgot we did this yesterday. I marked it in my notes, but I didn't remember which I marked it in my notes to do it. I didn't remember which day was supposed to be done. That's okay. So to build on this example here, we will do number 7, which is in the same along the same line of ideas with a twist. So number 7 says g of x equals, and over here I have x squared times 1 minus 2x. All right, so how do we treat this problem? So the problem, first of all, before you do anything, before you calculate any derivative or anything, you want to replace this formula here, want to replace that by a sum of powers of x. And that's very easy to do because you can simply say, oh, that's x squared times 1, which is x squared minus, and x squared times 2x is minus 2x cubed. So this is my function. It's not the answer to the problem. It's not the derivative. The derivative that I want to calculate is the derivative of this guy here that's underlined, which is going to end up being the derivative of x squared is 2x, and the derivative of minus 2 times the derivative of x cubed is, so it's going to be 2 times 3 times x squared. And that's 2x minus 6x squared. This is the derivative and the answer for this particular problem. So be careful, folks. When you have a product, you want to write that. Again, you want to distribute, use distributivity and write it as a sum of powers of x. And finally, we come to our number 11 over here. So number 11, which is the question that was asked, it goes as follows. So we have a function called r, f of r. Okay, so the letter is different here, but you get the idea. It's 5 over, what does it say, r cubed. All right, so how do we do this problem? Again, this is a quotient. Earlier, we just did a product. How do we do a quotient as a power? Well, we use algebra. And again, we don't want to write this expression. That's not the one that we're going to use. We're going to use algebra. And instead, we're going to say, well, this is the same as 5 times r to the negative 3 here, folks. So remember that it's very important to recognize. Remember in college algebra or pre-calculus when earlier, so you learn that when you write powers like that in the denominator, you write them as negative powers in the numerator if you want to switch them around. So this is f of r, and we can conclude here. We can now do the derivative, and f prime of r will be equal to 5 times negative 3, right, folks, times r to the, and it's going to be negative 3 minus 1, which is going to be negative 4. So I'm going to write that here, negative 3 minus 1. Remember that the formula is, again, and I'll remind it here, x to the n prime, and could be anything such as negative, a number like negative 3, is n times x to the n minus 1. So n being negative 3 in this case, what we get here is negative 4. So the answer is negative 15 times r to the negative 4. So that is the problem that we are looking at. Sam, does that answer your question properly there? All right. So this is okay. I lost the screen here. All right. So this is the solution to number 11, folks. Now, we did number 11, but my goal was also to do number 9, which is, kind of similar to this one. So let's do number 9 as well. So as you can see, my goal today is to do a bunch of these problems with powers of x, so you can you understand how to manipulate them. I took in increasing order from 5 all the way to 11, the odd numbers. Number 9 says here's a function g of t equals, and over here we have 2t to the negative 3/4. And I want everybody to also do this exercise and notice that g prime is equal to, and this is going to end up being, folks, this is going to end up being uh, 2 times, and then you take down this exponent, so you say 2 times negative 3/4 times t, and it's going to be that exponent, initial exponent, minus 1. So that's going to end up being negative 3/4 minus 1. All right. And this is the result of the derivative, which is not finalized. It can be simplified, and I expect you to simplify your answers, folks, on tests and such, because right now in calculus, you're expected to be able to handle simple manipulations of things like 2 times negative 3/4 over here, which really is negative 3/2 times t to the, and the exponent here is negative 3/4 minus 1, or if you want, negative 7/4. So this is the nice exponent and the nice formula, the nice answer to this particular problem. All right, so we got these done, and let's also do, as I promised, I want to do yet another example. So I took the numbers in increasing order, except for this one, which is a bit out of order. So there's one more problem that I want to do here, and that is number 13 from 2.3, before we move on to something else. So number 13, he says, here we go. So take care of this problem. S of p equals, and he says here, the square root of p minus p. Okay, so now this is not very useful to calculate derivatives because the formula would be too complex. So we're going to wipe this out. What is the problem here? The problem here is that we don't have all powers of p. We have this one here, the second one, negative p, but we don't have square root of p. So if you want to write a power of p, what you would say p, you will say p to the 1/2 minus p. That will be writing this thing as a power of p, folks. All right, so now I'm going to work with this underlined formula. So remember, everybody, square root is the 1/2 power. So I can work with this formula, and I can simply say that s prime of p, or s prime, is equal to 1/2, right, for this guy here, 1/2 times p to the 1/2 minus 1, which is negative 1/2, minus p to the first prime. This is going to be p to the 1 minus 1, or p to the 0 if you want, which is 1. Or just remember that p prime is 1. That's the derivative of function x, if you want. All right, so either way, this is the final answer. There isn't much you can simplify here, unless in the book, and I don't expect you to do that, but in the book they might say, and this is kind of nice to know, because again, since you're here in Calc 1, you're supposed to have mastered pre-calculus, college algebra, and such. So this is the same as 1/2 times, and p to the negative 1/2 can be rewritten as 1 over p to the 1/2. And since p to the 1/2 is square root of p, this is 1 over square root of p. So 1/2 times 1 over square root of p minus 1, which is the thing that I have here. So this is the final answer. That they might write it in the book like that. I don't know. I haven't checked. All right. So that being said, do you folks have any questions for me? So let's see. greatest common factors out like in number 5. Okay, so let me look again. So what is number 5? Number 5. Oh, there's the greatest common factor in 5. Let's see. Okay, so that. Oops. Who's 5? That's a good question. No, I wouldn't. No, I wouldn't take. So the question was if you would take the greatest common factor out. In number 5, indeed, there is a greatest common factor, which is 2, which you can factor and such. But in calculus, no, you don't have to do any of that. So you can leave the answer like that. Okay. All right. So in many problems, you might not even have a greatest common factor because of the nature of these derivatives. In any case, so let's move on to, okay, any other questions, folks, before we move on to something else here? So, okay, well, seeing there's none, let's move on. So we'll continue our lesson. So 2.3 is really 2 lessons, folks, here. And one of them is about, the general formula of the power rules and such. And then the other is about the product and the quotient rule. So we're going to do the product rule first. Now, the product rule is a very useful rule, but unfortunately, we don't have the tools right now to see how useful it is in practice, because all the problems that can be done with a product rule in this context could also be done with quotient, with regular calculations. So it's not that needed at this moment. So here's the deal. If you do, the product rule says, and I'm going to write it here, that if you do the product of 2 functions, f times g, and you calculate the derivative, that is equal to f prime times g plus f times g prime. So this is the product rule for this particular function. And why is it this way? So I'm going to explain you very quickly here, folks, just to kind of understand why this is the way you take the derivative of a product and not the incorrect way. There is an incorrect way. People think, well, because when you do the derivative of f plus g, all you have to do is to split up. So you do f prime and you do g prime, you add them up. Why is it not the same for the product? Well, because the product is quite different in nature when you calculate the limit. So remember that the derivative is a limit, and if you do the limit, so this is an explanation. I'm not going to ask you why this is on a test, but just so you have an idea of where it comes from, folks. So when you do the limit as x goes to, let's say, a number a, right? Of f times g of x minus f times g of a divided by x minus a. Well, that's not going to be easy to relate to the limit of f of x minus g of a times the limit of g of x minus g of a. So what people do, they take this expression here and they write it in the following trickier way. So they say f of x times g of x minus f of x times minus f of a times, I'm sorry, so let me erase here, minus f of a times g of x, that divided by x minus a, plus f of a times g of x minus, and then we're going to have minus f of a times g of a, all divided by x minus a. So this is equal to, and if you look here, you factor f g of x, so g of x times, so will be well, actually, so hang on a second. So let's put g of x at the end. So from this fraction, you could factor g of x. You can see that you got this factor, but I'm going to write it at the end here. So g of x times, and really you're left with a fraction f of x minus f of a divided by x minus a over here. So that's one part. And the second part, you factor f of a here. So there we go. So f of a times g of x minus g of a divided by x minus a. So when you pass to the limit, this is going to be f prime of a times g of a, and this other one is going to be f of a times g prime of a. So when you pass to the limit here, so that's why you get f prime g plus f g prime. That's the explanation. So with a little more care, you can make this rigorous, and that's your calculation. So this is why the product rule is true, folks. So remember that it's not that obvious. If somebody gives you a product of two functions, how do you do the derivative? Well, you gotta be careful. So you gotta take the first one first, take the derivative of the first function times the second, and then the first times the second, the derivative. So that is the rule. Now I'm going to apply this rule to a concrete situation. So let's say we have a function like x to the fifth, and you want to calculate its derivative. So obviously you could say, well, this is the power rule, and I'm done. So and I trust you that you understand that. So it's 5x to the 4. We know that. All right, so, but now I'm going to be kind of mean, and I'm going to say, you know what? How about you do this with a product rule to check if a product rule is actually true? It's got to be true in this case. If you write x to the fifth as a product, for example, if you write x to the fifth as x cubed times x squared, and you apply the power rule, the product rule, I'm sorry. If you apply the product rule, do you get the same answer? And the answer will be yes. So let's actually verify it together. So it's going to be x cubed prime. So my first function is x cubed. My second function is x squared. I think it's visible here. So it will be x cubed prime times x squared plus x cubed times x squared prime. And when you do this calculation over here, so now you need to apply the power rule for x cubed. So you get 3x squared times x squared plus over here you have x cubed times 2x. So remember x squared prime is 2x. So when you put these together, you will see that you get 3x to the 4 here plus, and over here you get 2x to the 4. So that all together is 5x to the 4, and that takes care of a problem. So you can compare and you can see, well, yes, indeed, we get the same result. And in fact, you could write x to the fifth as a product of any powers. And when you do the calculation, any powers that add up properly, right, to 5. And when you do the calculation, you with a product rule, you will see that you get the same result. So now, let's look and let's analyze the practicality of the approach here. So obviously the first approach is the one that really should be used, right, in practice. Why would I have to go through all this pain over here for the second approach if I can simply do the first thing? So in practice, I do recommend students to kind of look carefully and see which one is easier, which one is more straightforward, because you don't want to spend a lot of time and energy doing things that could be done, in a second, do them in a minute or something like that. So that's one thing that I want to point out. It's in this case, when you work with powers of numbers or like polynomials that can be distributed properly easily, you know, when you write them as power, the sums of powers of x, it's always convenient to to use that and not use the product. The product rule, however, has its own advantages in the sense that the world is not made up of powers of x only. There's other functions out there. Unfortunately, we did not discuss any other functions. We only have, if you look at the functions we discussed up to this point, it's only powers of x. It's either x cubed or x squared or x to the fifth or x to the negative 7 or x to the 1/2 for the square root and so on. So it's essentially powers of x. Is there something else that we would be discussing and it's not a power of x? Yes. It's the sine functions, the cosine functions, the tangents and such. But even those, in the grand scheme of things, if you think calculus 2, and in calculus 2 you will learn series, and those are also powers of x. Although infinite, sums of such powers. But even those are. And there's also some other functions that are not obviously powers of x. They can be written as series of such. And those are the exponential functions and the logarithmic functions. So there's a bunch of functions that are not in an obvious way powers of x. And that's where the product rule is most likely to be used. So for those types of functions. All right, so I'm going to do an example here from the book with a product rule. And I was telling you that if you look in the book, the problems that can be done with just manipulating powers of x are grouped as a first group there from 1 through 20 through 24. And then from 25 moving forward, you have problems that test the product rule and the quotient rule. So this is what we are going to address next. So I'm going to take a problem number 25, or let's do 26. How about 26? Let me give myself another page here. So number 26 of section 2.3. I'll leave 25 for you to do at home. You also have an answer for that. It's a homework problem. This one is a homework problem as well. U cubed plus 1 times 2u squared minus 4u minus 1. All right. So we want to do the derivative of this. This function is called b of u. I don't know why b, but it's just a name there. So that's fine. So the question is find b prime of u. All right. So as we said, we have two approaches, folks, two approaches. The number one approach would be to try to write out this product and then do derivatives of powers, and it's the simplest. So I'm going to do that. So I'm going to say, you know what, before I do any derivative, so I do preliminary work here, I'm going to do u cubed times 2u squared, which is 2u to the fifth, u cubed times minus 4u, which is minus 4u to the fourth, u cubed times negative u, which is minus u cubed, then 1 times 2u squared, which is 2u squared. So this is reviewing, if you want, your college algebra skills, folks. Then 1 times negative 4u is negative 4u. And finally, 1 times negative 1 is negative 1. We collect the like powers. So there's 2u to the fifth over here. Then there's minus 4. Oops, Okay, sorry about that. Minus 4u to the 4. I don't know why it leaves some mark here on the screen. Minus u cubed. All right, plus 2u squared. Oh, you know what? There is no overlap over here. I usually, so sorry about that. This is unnecessary. There is no no like powers here, folks. So all powers are different. I don't have to do any of that. So over here, I'm using this formula. This is not the answer. So the answer would be B prime, which is, I'm using this formula above, the one just boxed, and I'm going to say B prime will be 2 times 5, which is 10u to the 4, minus 4 times 4 is 16u cubed, minus 3u squared, plus 4u minus 4, and that will be minus 0, but I don't need to do that, so this is going to be my answer. And I recommend, folks, because of this, the nature of this online teaching, I recommend that when you go home, you know, you stop the video over there where I started the problem, and you think, oh, okay, so let me do this problem on my own. So just work out the problem, and then you can watch the explanation here. This way, we sort of compensate the, you know, the apparent lack of interaction. You know, and it allows me to make you know, videos without pauses, without a lot of pauses, and it also allows you to review at home the calculation. So that's how you do number 26. Now, this is just one way. The second way, use the product rule All right, the same problem. Now we expect a little bit of work, right? So extra work because this problem, look here. So it was just a step really. The second way would be a little bit of work. So we're gonna say that B prime of u equals, and now remember that we have two quantities, this one and this one. There's two quantities that we multiply. Those are gonna be my functions f and g. So B prime of u will be u cubed plus 1 prime times 2u squared minus 4u minus 1 plus, and then there's u cubed plus 1 times 2u squared minus 4u minus 1 prime. So we got this thing here, and that is that can be written as, and right now we can say, you know, let's take care of the derivatives. U cubed plus 1 prime, 3u squared plus 0, right? So we don't write the 0 there, just 3u squared times 2u squared minus 4u minus 1 plus, and over here for the second part will be u cubed plus 1. We didn't do anything to that. We just wrote it there, minus, and we're going to do the derivative of this guy. So which is going to be 4u minus 4. All right, minus 0, which would be gone. So this is not done. We're not done here yet because we didn't get to the, we need to get to the goal. Our goal is to do this thing here. So we worked a little bit harder here. We still need to work a little bit harder. So this is the product rule on the first line here. This product rule, this we wrote the derivatives appearing coming from the product rule. Now we're going to distribute these things and we're going to collect the like factors. So it's a little more work to do here. We're going to multiply now. So 3u squared times 2u squared is 6u to the 4. 3u squared times negative 4u is negative 12u cubed. 3u squared times negative u, or negative 1 is minus 3u squared. Plus, u cubed times 4u is 4u to the 4. U cubed times negative 4 is minus 4u cubed. 1 times 4u is 4u. 1 times negative 4 is negative 4. So we're not done, I told you. We're just going to collect the like powers of u. 6 plus 4 is going to be 10u to the 4. We have a negative 2u cubed here and a minus negative 12 minus 4 is negative 16u cubed. All right, so we have a, I'm going to underline the overline above here, u squared, and that's just that, minus 3u squared. How about u? That's 4u, and then there's minus 4. So there we go, we got the final answer with a little extra calculations here, so it's not as straightforward as the first case, but it works. So that's the idea of the product rule. All right, folks. Now I invite you, there's a couple more problems like this. Number 27. It's very similar to the one we just did, except that there's an extra twist, and I'm going to do that. So number 27 over here from 2.3, the extra twist is, let me write it out. So f of y equals, and we have 1 over y squared minus 3 over y to the 4 times y plus 5y cubed. All right, how do you do this problem? So either way, you are going to have to rewrite the powers. That's the idea here. Before you do anything, again, you want to rewrite this problem as, and instead of 1 over y squared, you want to write y to the negative 2, and instead of 3 over y to the 4, you want to write 3y to the negative 4. This is the key part of the problem, folks. So again, in calculus, what you want to do whenever you see negative fractions or radicals, most of the time what you would want to do is to write, instead of fraction, use negative exponents to write things without denominators, and radicals use fractional powers to write things without radicals, square root, cube roots, and things like that. Times, so that's going to be times y plus 5y cubed. With a problem written this way, I trust that everybody will be able to finish up the problem either by doing distributivity, which I invite everybody to do, or by doing the product rule, which again, I invite everybody to do. So this is going to be a homework problem. Please do it at home and let me know how that works out. If you're having troubles with that, do let me know next time. All right, so where are we headed now? I have one more thing to do here, and that is the quotient rule. Now, the quotient rule is slightly more complex, and it cannot be done in just 5 minutes. The explanation of why the quotient rule is true is very similar to why the product rule is true, maybe slightly more complex. So I'm not going to do that here, the explanation, but I am going to explain the formula, and we're going to stop here, and next time we're going to do practical applications of the quotient rule. So the quotient rule says, and this is going to be the last thing that we'll do here. The quotient rule says that if you have a quotient, obviously quotient, right, of two functions f and g, and you calculate their derivative, you're going to get the following thing. The denominator will be a slightly more complex one, will be g squared. So the initial denominator squared. This one goes here squared. The numerator will be like the product rule, but it will go like this, f prime g minus f g prime. Remember, for the product rule, you had f prime g plus f g prime. Now, there's a factor of confusion here for some students, and I want to clarify that before we move any further. So don't be confused. Like whenever people write things like this, x plus 1 over, because this is the situation that you'll see in practice. They start writing and they get the correct denominator, but then they say, which one am I starting with? Am I going to do x plus 1 prime times x plus 2 or x plus 2 prime times x plus 1? Because they seem to have forgotten that whenever you start the writing out the product rule, what you want to write the one with positive sign is the one that has the derivative of the top part. So this will be x plus 1 prime times x plus 2 minus x plus 1 x plus 2 prime. So again, remember, you always start with the top part prime. That is the thing that you do when you calculate the derivative. And, you calculate this, in this case, there's a bit of manipulations at the top, and you finish up the problem. Again, I'm not going to finish the problem here. My interest is to focus on the general formula for the time being, this one here. And pay attention, folks. So when you calculate, when you apply the product rule, again, so I'm discussing here about the philosophy of how to apply this. So there would be situation when you cannot avoid it. But if you look at the formula the way it is here, so it would be a miracle to apply the product rule to something like this, like x plus 1 over x plus 2 here. And why is this not working? Okay, so x plus 1 over x plus 2. So it would be a miracle to apply this and you get something much so significantly simpler. So that's not going to be the case. So this, whenever you apply the product rule, the quotient rule, to a quotient, the result will be significantly more complex than the thing you started with. So if there are other ways that you can employ to calculate the derivative, those would be my choice. So this would be my last resort. It's going to get things really messy when you apply the quotient rule. So that's the only problem with that rule. But it's a valid rule, and we are going to use it, employ it next time to calculate derivatives of some functions. Folks, I'm going to stop the recording here. I'm going to stop the lesson as well. If